Just going to adjust this here for a second. Okay, I think that works. Okay, so today, open up your lab manuals to page 33, and we're going to talk about sedimentary rocks. So these are rocks that have weathered or been broken down from other rocks and become something else entirely. And like it says in here, these rocks are the most abundant type of rock on Earth's surface. It says for the entire Earth, igneous rocks are most common, but most of them are covered by a thin veneer of sedimentary rocks. Okay, so we're first going to talk about the formation of sedimentary rocks, and we have a few things to cover here. We're going to cover the weathering, which gets into some processes here, the transportation, the deposition, and the lithification. All right, so flip over to 34, and we will start talking about how some of these rocks break down, how the process of creating a sedimentary rock is by taking one rock and transforming it into something else, right? So there are two ways this can be done, and we're first going to talk about mechanical weathering. So we talk about mechanical, we mean like you break a rock, right? You've seen me break rocks before. Yeah, so you take a rock and you break it. Congratulations, I've mechanically weathered it. And we also have chemical weathering. So we're going to talk about each of those independently. So mechanical weathering is when you break a rock down into something called clasts, right? And clasts are like groups of minerals, groups of rocks. And what these do is these break down into particles of various sizes. Okay, so these particle sizes are, we're going to talk about these here. What color do I not have up here? Let's go with blue. All right, so in the middle of page 34. All right, so what's going to happen here is you're going to have various particles of different sizes, right? And these are very important to know because these sizes can create rocks of different shapes and texture. You can have a rock that can look like this, right? To a rock that looks like number 27 in your sample kit. You are free to use those, by the way. And you can see that there is a defined difference between these rocks, right? So one, you can see little bits and pieces, and others, not so much. Not so much. All right. So when we talk about these particle sizes, right, there are four ways we break these down. And the first one we're going to talk about is gravels. Okay. So you walk outside, and you see a rock that seems to have other rocks inside of it, right? Like other rocks have like had pieces of it kind of put together. And it's usually pieces of gravel. And these pieces of gravel are usually 2 millimeters in size plus in dimension, right? Usually 2 millimeters. Okay. So these create rocks that have very dynamic textures. Okay, like this rock that I keep showing you guys here. It is lots and lots of pieces that have been cemented together. Okay. Next we're going to talk about is sands. Sands, all right. So in your manual, you see sands are 2 millimeter to 0.05 millimeters. Getting pretty small here. You go to the beach, you see sand, this is about what you're thinking. This is pretty close to what you're looking at. Have a piece of sandstone up here, but I don't know where it went. That's fine. All right. Oh, there's one right here. Number 30 in your sample kit, you will see red sandstone. And if you look very closely, you can kind of see the grains inside the sandstone. I'm not sure if you at home can see this here. Okay. See the grains inside this. And if you were to scrape it, yeah, you are able to handle the samples. If you were to scrape it, I'm not sure if yours has a penny in it. If you were to scrape it, you would get off some of the grains, right? Okay. So that's what sands are. That is about the size of a sand. Okay, next, the silts. And silts are 0.05 to 0.002, I'm sorry, these are all in millimeters, 0.002 millimeters. To give you an idea for silt, right? Have you ever gone into a river? You ever been swimming in a river before? Put your feet in it, it feels kind of like very fine grains there, you know what I mean? That's what a silt is. That's about the consistency you can expect. If you like go barefoot into a river or a body of water that consistently moves, not some ephemeral stream. But that's about what you can expect from that consistency. And yeah, they tend to feel very slippery. And the closest analog we can give you to these is like if you have flour. Silts are a lot like flour. Like if you have flour, the particle sizes are about the same. All right. And next, we have one more. And it's clays. And they are 0.002 millimeters to a single molecule. So 0.002 millimeters to a single molecule. These are very small. Very, very small. And clays, in particular, are sticky. Clays are sticky. They tend to like get themselves attached to other things. And this is how you get some that come together and create other rocks. All right. These are all part of the mechanical weathering process. Now, can you guys tell me the largest driver of mechanical weathering on Earth? If you have something that mechanically weathers a rock, if you could think of a way that this could happen, what would you think of? What's that?
Erosion.
Erosion's good. So when we talk about erosion, let's dig deeper into that. When we talk about erosion, what forces drive erosion?
Rain.
Okay, very good. That's a very good one. What else?
Sudden shift of the earth.
Think if you're, let's expand upon that. Think if you're in the desert and you see things moving. What process is making these move?
It's mostly sandy. It would be wind.
Wind, very good. So you have, water is the largest driver of erosion on Earth in one way or another. That also means glaciers. That also means rivers. But you can also have what are called aeolian processes, which are wind. Wind is also a very good one. And if I'm being completely honest, humans are a fantastic source of mechanical weathering because we alter the physical landscape as we so choose. And that can alter how the landscape develops over time. Okay? All right. So the next thing we're going to talk about is chemical weathering. Chemical weathering. So you mentioned rain. Rain's perfect. That was actually also going to tie into this. When we talk about water being the driver of erosion, that also counts for chemical weathering. So a lot of times what will happen, and you see this a lot with limestones in particular. Took a very neat class over the summer about karst. It's called karst geomorphology. And it is basically landforms and things that are created due to weather breaking down, the acidity in the soil and the rain, breaking down rocks over time. And this is a perfect example of chemical weathering. That's exactly how this works. So let's look into the book. This is the middle of page 35. And while mechanical weathering is all about breaking something down through a physical process, this is one that is talking about breaking something down through a chemical one. And I know that's a very simplified explanation, but it is one thing reacting with another to break down a rock. So, and it says here about water and oxygen are chemically very reactive. They're very reactive. So do you remember when we did the mineral identification lab? And I showed you, let's pull it out again. Pull this thing out here, right? So, remember when I showed you the scratch plate and number 12 in here? Yeah? Okay. And I showed you how that worked, right? Okay. We know that this is a form of iron, right? But the question is, why does the iron do this? Why does the iron do this? Do you remember we talked about this? And what Go ahead.
I can remember what it actually is.
What causes
Oxygen.
oxygen? Very good, very good. Yes. So oxygen is a fantastic driver of weathering in one form or another, because oxygen is a very, at its core, is almost a very corrosive gas in a way. It breaks things down over time, and coupled with water, you find that one rock can become something completely different when exposed to both of those in large amounts. Right. And we know that this process of chemical weathering, when you take oxygen and making something into something else, is oxidation. Oxidation. All right. Okay. So remember that mechanical weathering is about actually breaking something, right? It's about taking a rock. It's about taking a rock and putting it against another rock, right? See the pieces that are coming off of that? I have now mechanically weathered this rock. Okay? But in the mineral identification lab, we talked about how we can take hydrochloric acid and apply it to a rock, right? And what that will do is, under the right circumstances, it will break down pieces of that rock and turn it into something else. Okay, and that is a chemical weathering process. So, all right. Next thing we're going to talk about, let me mark these off as I go for the people watching at home. So we talked about formation through mechanical, particle sizes, and chemical weathering. And next we're going to talk about transportation. Okay, so for rock to be deposited somewhere where it can become something else, right? That rock has to somehow be moved somewhere, right? When you apply water, coming to rain. Rain's actually a fantastic, very simple thing for us to grasp, right? So when you have rain that comes down on a rock and it slowly wears it away, the water still flows. So it goes somewhere else, right? So basically what that is that water is transporting the sediments that it is pulling off of that it might even be chemically weathering it, to somewhere else, to be deposited elsewhere, and maybe even to become something entirely different. And that can happen through two different ways here. On page 36 in your lab manual, we talk about the transportation of ions in solution. So when you have a chemical weathering process, what it can do is it can take these ions and take them somewhere else, and that is called the solution load. That is what that is. It's a solution. And I'm not very good at chemistry, but we know that a solution is a mixture of one thing into another, correct? Something that suspends something in it. So, dissolved ions, it says here, also give water its flavor, which is a really strange detail. But, all right, given that I'm not sure what. Okay, we're not going to. I digress. All right, so we're also going to talk about the deposition of sediments. So when you take this weathered rock, right, these little bits of weathered rock, whether they be the size of a gravel, a sand, a silt, or a clay, okay, and these go somewhere, they have to end up somewhere. So have any of you been to a river delta, right? Have you ever a river delta is where the mouth of the river comes out. And what happens is when it empties into the ocean, it also brings down a lot of very fine sediments, and they will usually deposit there, and you usually get these very dynamic fluvial formations. So this is what I mean by the transportation, the deposition, is when you transport these sediments and they finally run out of steam and finally find a place to lay. They are transported there, and that is where they sit and gradually begin to build up over time. And eventually, we lead into our next process called lithification. So, after you have weathered the rock, after you have transported the rock, it has to go somewhere to become the next thing that it wants to be, right? Or say wants to be, it's going to be. All right, so we have lithification. Lithification. Lithification can be broken down into two sections. Get another color. All right, so we have compaction. people at home see this. It's kind of light, but I won't do. All right, the compaction. Compaction. So you see at the bottom of page 36, compaction states that it happens when sediments are squeezed together, right? So it says freshly deposited sediments like that of tiny particles and silt and clay, and that typically contain a lot of airspace, accumulate. And what happens is the sediments squish together and get compacted. And you get, we're actually going to go through a few of the samples. Additionally, you have sedimentation. All right. So this happens when particles are glued together. Think cement, right? You take cement, put it down there, it's going to harden, it's going to become something else. This is what cementation is. And it says here that these mineral cements are formed by the recrystallization of ions in a solution. So this tells you that cementation has a lot to do with chemical weathering. Okay? Common mineral cements are quartz. Quartz, look at sample number 3. Sample number 3, quartz, yeah. A cemented mineral, right? And the iron oxides, like the hematite that I was showing you. And it says sample number 29. And this is a gravel sediment. Now, actually, let me go back to this large conglomerate right here. This is cemented rock. Okay, that's what this is right here. You can see that it has very large particles, but also a lot of it is cemented together. And this is how this process works. They were glued together to create this very dynamic shape. Now, it's actually pretty cool on the underside too. It's got some very neat rocks in there. All right. Okay. So to review again, we weather it, whether it be mechanically through a physical process or chemically through a chemical process, breaking it down to its ions. Then we transport it, and that is through water, typically through water, sometimes through air. Who knows? We could even take a rock, pick it up outside along the Diga Trail, go over here behind Martin Hall and pitch it into the woods. You have now transported a rock. All right. And then when we do transport that rock, it becomes something else. And that's what we lithify, right? There is one last thing to talk about, and that is organic precipitation. You will see this at the middle of page 37. So there is a very important life form on Earth that does exactly this, that can sometimes take minerals out of, and I'll even give you a clue here, out of seawater and turn it into something else. Do you have any idea what those are?
Shellfish.
Very good guess. That's actually, yes. Let me give you another hint. We need to save these things. You often see campaigns about like, save this. The Great Barrier Reef. Reefs in particular, they will take sediments out of the water and use the sediments. And yes, shellfish also do this to various respects. But I really like plugging for the reefs because we need to be good stewards to this planet. All right. So now that we have gotten through all of these, we're going to go through a few very simple identifications. The samples in this kit are, they're pretty good. If I feel one isn't quite good enough, I will give you another. But this is going to lead into your lab. This is going to lead into actually doing your lab. All right. So the first one we're going to talk about is a conglomerate. So it's an elastic rock composed of gravel-sized fragments. I've been showing you guys this all day. Yep, this is a conglomerate. This is something that has various different types of sediment sizes, and typically this was formed in what we would consider a high-energy environment. So for water to transport large pieces, pebbles and pieces like this, of this gravel, would take a lot of energy. So what I mean by that is it's probably flowing very quickly. I would venture to say that this probably came from maybe the Coosa River, something like that. So we're not talking like you're not going to go down to Ladiga here and that little underneath that bridge right there where they got a little stream. You're not going to find stuff like this typically. All right. And next we're going to go over to page 38. Sandstone. So that's number 30 in your kit. I showed this one before. This is red sandstone. Okay. And are composed of sand-sized particles. And if you like scrape it a little bit with your finger here, kind of rub your thumb across it, you can feel that. You might even have some of them come off. And this indicates moderate energy transportation. So it didn't take a lot of velocity from the water to get these where they needed to be. Okay. And it says here they are cemented together by iron oxide, giving them their red color. All right. Okay. Next, we're going to go to argillaceous sandstone. These are primarily made, this is 31, I'm sorry, 31, primarily made from sand. But instead of the iron oxide gluing them together, this is from clay. This is from clay. All right. Yep, and it tells you that the word argil means clay. So, all right, number 32, argillaceous shale. So shale's pretty common. We're on the middle of page 38, by the way. Shale's pretty common, and they are composed of a mixture of silt and clay. Silt and clay. Let me get a little closer there. Try and get a good view of that. All right. Okay. And it says, rub your finger along the rock, and notice that it feels very little. You feel very little resistance. You don't get like the pieces of sand that you had with the red sandstone. It's almost a little smooth. You can feel just a little bit of smoothness there. All right. Okay, 33. Limestone is a chemical sedimentary rock composed of at least 51% of the mineral CaCO3, calcium carbonate. So, calcium carbonate, not carbonate. Wow. Too much Star Wars in my life. All right. And you'll notice that a lot of these say that to be considered to be classified as this rock, they must contain at least 51% of that mineral. So you will see here that in the lab manual, it says that it needs to be at least 51% calcite. So, all right. And it says, look at it. And it is composed almost entirely of broken pieces of seashells and other marine organisms. Limestone is one of the few minerals that are produced through organic processes. And this is where you talked about shellfish. This is where we get some of these. Yep. It's a very good observation. All right. So number 34 is dolomitic limestone. Dolomitic limestone is this one right here. All right. Okay. You will not notice any shell fragments, no fossils, no nothing. And basically what this means is after deposition, it says here some of the calcium in this rock was replaced by magnesium. Magnesium instead. And making it dolomitic. That is not a term you need to know on your test line. Oh, it's backtracking us. That's fine. Number 27, chert. Okay, this is what happens when you weather quartz. Yep. This quartz has an inorganic origin, and it's usually found in rounded masses named nodules. I have a very good example of this. Hang on. One second. We're getting there. I'm going to show you guys a cool nodule. Yeah, look at that thing, right? Pretty cool. Yeah. So, this mass here that has been just vibing in the back of the lab, it's a nodule. And this is what these look like. I don't think this is particularly quartz, but this is what a nodule would be. So, I wanted to give you a visual for what this might be like. So, because of the way these fracture, and remember we talked about fracture and cleave. So fracture means that they tend to fracture in sharp edges, we can make arrowheads out of these. And this has been done for many centuries before. All right. And last but not least is bituminous coal. This is a chemical sedimentary rock. Show this one here. Kind of shiny. Yeah. Okay, so the difference between coal and what we have been working with previously here is that coal is made from wood and other plants, parts of plants. And usually how this works is these trees and plants fell into stagnant water or standing water, and eventually what happened is they lithified, and they basically became compressed by everything that came on top of them. So, all right. We're going to head into the lab here, and what I'm going to do is for the people at home, I'm going to go through some of the samples. Give me 1 second here. I'm going to put together the samples I would like you to pull. All right. What I would like you to do is the inserts in your lab, in these things here. Yeah, don't use the inserts here. Oh, dang. Okay. This one. Okay, you are going to answer questions about these rocks, about these 5 rocks. Let me see. A will be A, B, C, D, A. All right, and that will be the rocks you will use for your lab. Okay? All right. For those of you at home, I'm going to step you through this using the kit that I have here. Actually, I'm going to take it on the kit because I'll give you guys my samples. All right. Okay. For those of you at home, all right. So, chair over here. We'll get another conglomerate. So feel free to observe these rocks as you so choose. And answer the questions about them if you would like. Put all right. Actually, yes. Show me what you got. Okay. Write them down in your lab manual and take a picture and send them to me again. Yep. Thank you for letting me know. All right. So, for those of you at home, let's go through this. All right. So, this is sample 27. Let me pull this a little bit closer. This is sample 27. All right. Move this rock. Okay. All right. It is going to ask you, sample A, it's going to ask you to identify it. And under what conditions of transportation or deposition did these sediments accumulate? So look at the size of the grains. Look at the texture. Okay. That's 27. 27. All right. I'm sorry. Question 1. Sorry. All right. Okay. Or sample A, sorry. Sample B, sample B. This is sample B. Observe sample B. All right. Okay. Sample C. Sample C. Right here. Sample C. Observe the size of the grains. Maybe the color if you'd like. All right. Okay. Sample D. Sample D. It's right here. All right. Notice the color, texture. Okay. And sample E. Sample E. All right. All right. Very good. Okay. All right. So if you have to, going back through the video, take a look and stop it if you need to. But from here, I'm going to say good luck. And if you have any questions, send me an email.